Hello, I'm Josh Gluck from the College of Wooster. I've created a voiceover Khan Academy style presentation where I explain and demonstrate the Claisen ester condensation. I will draw and narrate chemical properties and reaction schemes over this dry erase board. This reaction fits into the wider scope of carbonyl chemistry. It is used to form new carbon-carbon bonds between esters to create a beta-keto-ester product. This reaction can occur within a diester to create a cyclic molecule and can also be used with other carbonyl groups besides esters. Now before we go any further, let's first talk about some key terms that you'll need to know when discussing these reactions. I'll define them over the course of this presentation. These terms involve the enolate ion, alpha hydrogen, pKa, the difference between an electrophile and a nucleophile, carbonyl groups, an ester, and cyclization reactions. First, let's talk about the formation of an enolate ion. Let's say we have an ester, methylbutanoate. When methylbutanoate is deprotonated by a strong base like sodium methoxide, the conjugate base, known as an enolate ion, forms resonance structures which have a stabilizing effect. The carbonyl pi bond can shift over to form the bond between the alpha carbon and the carbonyl carbon. An acid strength can be characterized by the stability of its conjugate base. This is why methylbutanoate has a pKa of 20, but butane, which forms no resonance structures, has a pKa of 50. Recall that the pKa is a measurement of a chemical's acidity. Chemicals with a lower pKa are more likely to donate protons. It is important to note that only hydrogens from the carbon adjacent to the carbonyl have this character. These hydrogens are known as alpha hydrogens. This is because this is the only carbon that can be stabilized by resonance when deprotonated. So now that we've created this enolate ion, what do we do with it? The answer is the Claisen ester condensation reaction. When we form this enolate ion by deprotonation, we've created an electron-rich region at the alpha carbon site. This region is more likely to react with the electron-poor regions. So, by definition, we have created a nucleophile. And what do nucleophiles react with? Electrophiles, in other words, electron-deficient regions. If we take a closer look at the carbonyl carbon on methylbutanoate, we can see that it has some electrophilic character due to the resonance structure that it forms. There's a partial positive charge at the carbonyl carbon, meaning that it is electron deficient. So what we can do is react the enolate ion of methylbutanoate with another molecule of methylbutanoate that hasn't been deprotonated yet. So we get a nucleophilic attack on the electrophilic carbonyl carbon from the alpha carbon. To maintain the octet rule, electrons from the carbonyl pi bond move to the oxygen. Now you can see we have just formed a new carbon bond in this intermediate structure. This alpha carbon has formed a bond with the carbonyl carbon, which we can now call the beta carbon. This is because it is in the beta position adjacent to the carbonyl group of the attacking molecule. As you can see, we still have this methoxide group bound to the beta carbon. Methoxide typically isn't a good leaving group, but the reformation of the carbonyl group drives this activity. The carbon-oxygen double bond is much more stable than the bond between the oxygen in methoxide and carbon, and so we have formed our beta-keto-ester product. There's a ketone at the carbon next to the alpha site where the carbon-carbon bond was formed. As I mentioned before, we can call this carbon the beta carbon. One thing I should mention about this reaction is selecting a base. In this reaction, I picked sodium methoxide because there is an alkoxide at the carbonyl carbon. Alkoxides are strong bases, but they are also good nucleophiles. So, methoxide could potentially substitute the alkoxide at the carbonyl carbon. But since the alkoxides are the same, any substitution is negligible. So it is important to select a base which matches the ester's alkoxide. If you noticed, this entire reaction occurs because of deprotonation by a strong base, sodium methoxide. All other instances of bonds forming and breaking are due to resonance structures and stability, so the reactions that occur are reversible. And so we now know the mechanism of the Claisen ester condensation. There are a lot of things that we can do with this mechanism beyond just reacting a molecule with itself. If we have a diester, we can have an intramolecular reaction. When a Claisen ester condensation occurs within one molecule, we call it the Dieckmann cyclization. And so this reaction occurs in the same way that we just saw. with a deprotonation from a strong base that matches the ester R group that creates a nucleophilic enolate at the alpha carbon site. The main thing to consider with this reaction is that it will only really occur with 1,6 diesters or 1,7 diesters because these molecules will form 5 and 6 membered rings accordingly. These rings have very little ring strain and will make stable products. However, 1,5 diesters would create a 4-membered ring. The ring strain of a 4-membered ring is greater than the nucleophilic electrophilic interactions between the alpha carbon, so it would be more favorable for the 1,5 diester to react with another 1,5 diester molecule. Now, what's interesting about this reaction mechanism is that it can be used with more than one molecule. This brings us to the crossed Claisen condensation. If I take two different esters, I want to make sure they only form one product. So if I set up a reaction with multiple sets of enolizable hydrogens between the two molecules, I'll form a mixture of products. This isn't very helpful since I'll have to do extra work to isolate the product I want. So in a careful crossed Claisen condensation, there should only be one set of enolizable hydrogens. This way, only one new nucleophile is created. In the example I've drawn here, there is only one source of enolizable hydrogens. On that note, you should use two esters with the same alkoxide to avoid unwanted substitution by the nucleophilic base. Both esters I have drawn here have a methoxide connected to their carbonyl carbon. And now, by following all of the rules I've set for myself, I've only formed one product between the two esters. It is important to keep in mind that you can use different carbonyl-containing molecules. Both ketones and aldehydes have a strong electrophilic site at the carbonyl carbon, which is susceptible to nucleophilic attack from enolate ions. If you do choose to mix esters and other carbonyl-containing molecules, make sure to follow the rules I just listed, and consider the differences of acidity between the two molecules. That will determine which enolate ion will form, and therefore determine what product you will form. To wrap up this lesson, I want to summarize some of the key takeaways. First, any Claisen-ester condensation reaction requires the formation of an enolate ion, which is made possible by the stabilizing resonance structures from its carbonyl group that creates an acidic alpha hydrogen. Next, the nucleophile-electrophile interactions characteristic of carbonyl chemistry guide the mechanism of the Claisen-ester condensation reaction. Additionally, when performing crossed Claisen reactions, carefully set them up so that only one product is formed. Lastly, the success of the Dieckmann cyclization is dependent on the ring strain, or lack thereof, in the product you are trying to form. Generally, this reaction will only be successful with 1,6 or 1,7 diesters.